All right, so this is our second video in colligative properties, and I'm starting with the third slide. Let me pull up my visualizer here. We're starting with the third slide in the colligative properties PowerPoint. Okay, Raoult's law. This is vapor pressure lowering. I feel like changing my marker. Let's do purple. I do need paper. They get mad if I write on this. It won't come off. Although these are Crayola. Oh, they're washable. I could get away with it. All right, Raoult's law is about vapor pressure. Sometimes I will abbreviate this VP for vapor pressure. So just so you know, and it is Raoult's law. I'm not too keen on having you guys memorize all of the names, but it is helpful because sometimes you'll have the Raoult's law constant. You'll have that given in the problem, and so if you can relate that to vapor pressure, you'll know how to solve it. Or if you see the phrase vapor pressure, if you can connect that to Raoult's law, then if you have like a formula sheet for your homework and your exams, you know exactly where to go. So while I don't quiz you over just names of things, it's useful information. It will help you on your exams. It will help you with your speed because you'll know exactly what type of problem that is. You'll know exactly where to look in your notes or preferably on a formula sheet. Okay. All right, so vapor pressure is the pressure above a solution of the liquid in the vapor phase. What is going on? Okay, so let's say you have methanol. This was an issue in some hand sanitizers. We had a hand sanitizer shortage due to the COVID-19 global pandemic, kind of a big deal. And methanol is a toxin. There's an old wives' tale that a thimbleful, if you drink a thimbleful, which is about the size of the tip of your thumb, of methanol, you'll go blind. So it's a dangerous thing. You don't want to be exposed to a lot of this. It's also called wood alcohol. So if you ferment cellulose wood, that's what you get. Okay, so the vapor pressure of methanol is, again, the methanol molecules in the gas phase above the liquid methanol. And I'm going to write it like this, CH3OH and then L for liquid. That's supposed to be an L. That doesn't look really good. L for liquid. Sorry about that. Okay, so that's what the vapor pressure is. So something that is what we call volatile, this is a little $5 word here, volatile, in regular parlance or the way we normally speak, volatile can mean angry or almost explosive. In chemistry, technically, it's a term that does not mean explosive, but it's something that evaporates easily. So this is a liquid or a liquid solvent that evaporates easily. Quickly, easily, I'm going to be a little imprecise with my terms just so that you understand. Although quickly doesn't always mean easily. We're talking about kinetics versus thermodynamics, but that's like 5 chapters away. So we'll just learn this general definition. So if you had a cup of acetone, which is often used as a nail polish remover, next to a cup of water, and you can do this experiment, just don't like hover over the acetone and like inhale it or anything. It's not good for you. If you do this experiment, what you'll notice is that the water sticks around a lot longer. So what you're going to see is the amount of acetone dissipating. It's evaporating at a much faster rate. It takes a lot less energy to make that transition from liquid to gas. Okay, so something that's very volatile has a high vapor pressure. Whereas something that is not very volatile, and I like to use water, if you leave a cup of water on your bedstand overnight, hopefully you don't have pets that knock it over, if you do that, we have water. I'm going to draw fewer dots to indicate if the circles are water in the gas, if this circle is water gas, and down here is water liquid. So I only have 1, 2, 3, 4 just representing fewer water molecules in the vapor phase versus methanol. Methanol, and I can even add methanol, is quite a bit more. right? So if the purple dot is methanol in the gas phase, just from this picture, you can see that. How would we look this up in a table? You would look up just what is the, you could actually look at what's the enthalpy of vaporization. And if it's a smaller number, that's something that's going to be more volatile. If it's a very large number, that means it takes a lot of energy to get from liquid to gas phase. So we could also look up the enthalpy of vaporization or evaporation to check that out. Okay, so that's just vapor pressure. Raoult's law is the law that summarizes this observation. When you add impurities or a solute, you could also call it a solute, to a liquid, the vapor pressure decreases. That's because the solvent molecules are interacting with those particles, and there's some attractive force between the molecules in the liquid phase and any solute or impurity that you add. So when you add a solute or an impurity, that liquid, the molecule in the liquid phase, is actually getting tied up. I think of it as being tangled up or tied up with these particles that we've added. And so it's not readily converted to the gas phase because there's something else going on. It's like trapping it in the liquid phase. So what's important to note is that when you increase the amount of solute, the vapor pressure decreases. If you remember that, it makes this formula a little bit easier to remember. So here's the formula. I can spell, really, I promise. Okay, so the pressure, this is the vapor pressure, let's say VP, of the solution, SOLN is my shorthand for solution, is equal to the mole fraction of the solvent times the vapor pressure of that solvent, not solute. Okay, I don't have solute, how much solute. The paradigm, or what we're looking at for this formula, is the mole fraction of the solvent, not solute, not what we add. This is the biggest mistake that students make on exams, is they'll think that that's the mole fraction of your solute. So this should be a pretty big number, close to 1. Usually it's more than 0.5, more than a half. The other way I remember this is, okay, the mole fraction of the solvent is going to go down the more I add, right? The mole fraction of the solvent. So if this is pure solvent, no impurities, pure solvent, whether it's water or hexanes or methanol or ethanol, pure solvent has a mole fraction of the solvent equal to 1, meaning 100% solvent. It's 100% solvent. So the vapor pressure of the solution is the same as the vapor pressure of the pure solvent. If my solution is pure solvent, then the vapor pressures of the solution and the solvent are the same. The mole fraction is 1. Okay, let's say I have 95% by moles, not mass. Then it would look like that. That would be my mole fraction of the solvent times my vapor pressure. Let's say it's 1.2 atm of the solvent. That means I just multiply these. I need to get a new calculator. The vapor pressure, whatever unit you plug in, on one side is the unit of, and it's a gas, right? Pressure means gas, so it's going to have a regular unit of pressure, whether it's atmospheres, mmHg, torr, bar, Pascal, any unit of pressure. But whatever you plug in on one side, it's going to be that on the other. So we don't have a constant in this one, but we do have vapor pressure of solvent, and that varies with temperature, right? If you heat something up, what do you think happens to the vapor pressure? Are you going to favor gas phase or liquid phase? Right? Think about it. Heat something up. What happens? Does it evaporate? And so what does that mean to the vapor pressure? Okay. I have a link on here that you can copy and paste into your browser and kind of click through. It has a nice animated image. So I encourage you to pause the video and look at that. And then we're going to work through an example. All right, so the example in the slide is vapor pressure of an aqueous, meaning water-based, solution of urea is 291.2 millimeters of mercury. The vapor pressure of water at that temperature is 355.1 millimeters mercury. And the question is, calculate the mole fraction of each component. Okay, so a little bit of a twist. We're given both of the vapor pressures. They are in the same unit, which means I don't have to convert. That's nice. Okay, so I need the mole fraction of my solvent on one side, right? So this is my, solution, excuse me, MMHG. I need the mole fraction of solvent. Remember, that's what I'm solving for in the formula, okay? And the vapor pressure of my pure solvent, which is water, is 355.1 millimeters of mercury. All right. The question's asking me for the mole fraction of solvent and solute, each component. So I'm just going to divide both sides. Wow, really? Okay. Sometimes it's hard for me to talk and write. You picked up on that already. All right, so that's the mole fraction of the solvent. And it is unitless. Mole fractions are unitless, just like mass fractions are unitless, because you're dividing by the same unit. Okay, my calculator died. Actually, it didn't die. Somebody borrowed it and didn't give it back. Wah, wah. So plug that into your calculator. That's the mole fraction of your solvent. How do you get the mole fraction of your solute? It is simply 1 minus the mole fraction of your solvent. That equals the mole fraction of your solute. All right, so solve that. You can check your answer by adding the two numbers up and make sure you get 1. It might be 1.000 or 0.99999 if you have irrational numbers, which you probably will. And so it might not be exactly 1.0 perfectly to 7 significant digits, but certainly within, I would say, 2 to 3 decimal places. You should have something really close. Okay, so that's Raoult's law on vapor pressure lowering.